All right, today we're looking at Lagrange error. Now, if you've been following all the videos in this unit, I'm sorry for the lower quality for the first few. They were made a few years ago and haven't remade them yet. I will be remaking them within the next year. Granted, for those of you that are watching for this year's calculus, probably won't help you. All right, so today we're looking at Lagrange error. Now, this is a lot of information. I'm not expecting you to know all of this or write all of this. It's just background on where we get the Lagrange error bound. So Taylor's theorem says that we can create a polynomial, and if we stop the polynomial, it has some remainder. That remainder is going to be the n plus 1 derivative at z of x minus c to the n plus 1 over n plus 1 factorial. So there's some value where the next terms would equal the remainder, whatever's left over, the error in our approximation, if you will. Now, a consequence of that is we can find an error bound even if a series is not alternating or decreasing, as long as we can find the max of the next derivative. Okay, so as long as we can find the max of the next derivative, where that max is only between x and the center. So let's look at an example of this. We have this series right here. F of 2 equals 6, f prime of 2 equals 4, f double prime of 2 equals -7, f triple prime of 2 equals 8, and we want the third degree polynomial for this information. So, should be a pretty easy setup. F of x is going to be approximately 6 plus 4x minus 2 minus 7 over 2, x minus 2 squared, plus 8 over, what would that be, 6, x minus 2 cubed. We'll simplify this down to 4 over 3, x minus 2 cubed. And we want to use this to approximate f of 2.3. All right, so if we plug this into the calculator, we get f of 2.3 is approximately 6.921. Now, if you're doing this to prepare for the AP exam, know that it is very rare for a problem like this to show up on the calculator section. It's more likely to show up on the no calculator section. All right, so then in part B, it tells us the fourth derivative of f satisfies the inequality f, the fourth derivative of x, is less than or equal to 9. Well, this looks a whole lot like a maximum. This is saying the fourth derivative of x is going to be less than 9. Its maximum value, maximum possible value is 9 on the interval 2 to 2.3. Well, that means if we use that error bound from the other page, our error is going to be less than or equal to the next term. So x minus 2 to the fourth over 4 factorial times the max of the fourth derivative of x. Now, we don't want it with x though. We want it with our value we're trying to approximate. So this is going to be 2.3 here, and this is going to be 9. So we have this error is going to be less than or equal to 0.3 to the fourth over 24 times our maximum of the fourth derivative, which is 9. All right, and if we plug that in the calculator, we get 0.00304. Okay, so our error has to be less than or equal to 0.00304. All right, so sometimes they will just give you what the max is. Sometimes you'll have to do some work to find it. So in this one, we want to create the polynomial for sine of 5x plus pi over 3 with the third degree. Now, take note, this cannot just be substituted in for the Maclaurin series for sine because they don't align. If we plug in 0, we get sine of pi over 3. If we plug in 0 to our Maclaurin series, we get sine of 0. Not going to align there. All right, so what we're going to do is we're going to find our derivatives. F of x is going to be sine of 5x plus pi over 3. F prime of x is going to be 5 cosine 5x plus pi over 3. The second derivative, this is 25, negative 25, sine 5x plus pi over 3. And the third derivative is going to be negative 125 cosine 5x plus pi over 3. And then we can create our polynomial. So p of x is going to equal, we're going to plug in 0 to get this. Sine of pi over 3 is root 3 over 2. Plus cosine of pi over 3 is 1/2, so 5/2 x, and there's no center 0, so just x. Minus, plug in 0 again, get sine of pi over 3, so that's root 3 over 2 times 25. So 25 root 3 over 2 times x squared over 2. So that could be 25 root 3 x squared over 4. Minus, plug in 0 again, we get 125 over 2 times x cubed over 6. So it says 125 over 12. Okay, so here's our polynomial. Notice this is not an alternating series. So alternating series error bound wouldn't work for this. So in part B, when it says use Lagrange error bound, we don't even need that information. We know it's got to be Lagrange because it's not alternating. And we want to show that this, which is the error at x equals 1/15, is going to be less than 1 over 1200. So it's going to use some Lagrange error. So we can have f of 1 over 15 minus p of 1 over 15 is less than or equal to, well, we have the general term for the next part. So we have 1 over 15 to the 4th over 4 factorial, which is 24, times, and then the maximum of the next derivative. So 4th derivative, that's going to be 625 sine of 5x plus pi over 3. And in the last problem, where it didn't tell us, or where it told us what the max is, this problem it doesn't. But luckily, we're using a function we know the max of. We know that sine of 5x plus pi over 3 has to be less than 1, less than or equal to 1. It'll never be bigger than 1. So that means this is a maximum of 1 times 625. So our max of that next derivative is going to be 625. All right, and you can do some simplification here. You're going to simplify some things down. If you simplify it down correctly by hand, because this would be a no calculator problem, very ugly no calculator problem, but a no calculator problem. You get that this is equal to 1 over 1944. Now, if we look back to the question was asking for us to show that this is less than 1 over 1200. So this is less than 1 over 1200. And so we've shown that using the Lagrange error bound. Okay? Let's look at another problem like this. And this would be day 2 if you're in my class. So this is the day 2 part of the video. All right, so now we're looking at some alternating series problems. The Taylor series for x equals 2 is for a certain function, converges for all x in the interval of convergence. The nth derivative of f at x equals 2 is given by that value. So that will give us the nth derivative, and f of 2 is 1/3. Write the second degree polynomial for x equals 2. Well, this is just our normal process, except instead of actually finding the derivative each time, it already tells us what the nth derivative is every time. So f of x is going to be approximately f of 2, which is 1/3, plus, and then now we're looking for the first derivative. So the first derivative of 2 is going to be negative 1 over 3. So plus, well, that'll be minus 1 over 3 x minus 2. Then we want the second derivative, because we want the second degree. Second derivative of 2 is going to be 1 over 9. So plus 1 over 9 x minus 2 squared over 2, which will give us over 18. There's our polynomial. And then we want to show that this is going to be, for as x approaches, we want to show that this polynomial centered at 2 approximates f of 3 with an error of less than 0.01. Now, it didn't say anything about the series alternating, but we can see as this degree goes up, this term is going to keep alternating between positive and negative. So this is an alternating series. So we know our error has to be less than or equal to the next term of the polynomial, with 3 plugged in. So next term is going to be the third derivative, which is negative 1 over 3 cubed, which is 27. Negative 1 over 27 times 3 minus 2 cubed over 3 factorial. So just the next term, technically the absolute value of the next term. We simplify this down, we just get 1 over 27 times 6 gives us 162. 162 is definitely less than 1 over 100, which is what 0.01 is equal to. And so we've shown that the error is going to be less than 1 over 100. So it's just alternating series error problems. Okay, there's one more type of problem I want to look at, and I really just want to get you started on it. So this one is not an alternating series. If we look at the terms here, positive, negative, negative, positive, not alternating. So this is going to be a Lagrange error bound. Now, let's just look at this last part down here. Use the information from the graph of y equals the fourth derivative of x to show that this error is less than 1 over 8. Well, we said it's not alternating, so we have to use Lagrange. So since it's the fourth derivative, we know that our next term would be x minus our center to the fourth over 4 factorial, which is 24, times, and then the maximum of this fourth derivative. Well, this seems a little weird, but if we look, this is an increasing function with a maximum value at 7. So that means the maximum is going to be 7. And then we can actually plug in the x we want. We want 2.8, so we'll put 2.8 here. And then we would simplify it down. If we simplify it down properly, we get we get 0.119, which is less than 1 over 8, which is 0.125. Okay, and so we can see how this might be another way they ask something for Lagrange error. I'll let y'all go and find A and B on your own, but that's all it's asking for there. Okay, let me know if y'all have any questions. Y'all have a great day.